Oh, I'm live. Chat, we are live, as the kids say nowadays. Mm. Uh, what has been new with me? Well, it has been 9 months since I made my last appearance on the internet, and many things have happened. I'm now a college student. Surprise, surprise. That is indeed how time works. I have been doing a lot of preparation for future research for um, becoming, I don't know, some type of scientist, some type of physicist, or a researcher at some um, large company in the future. Although that's not really necessarily what I actually want to do. I think more generally, I'm just skill building for either becoming a startup person or just doing some research. But I think regardless, it's important to have some degree of a strong technical background to navigate the future, especially with many skills being more or less replaceable. You need to like have a good arsenal of things that are actually important. And so, being good at math, I believe, is one of them. Maybe you can disagree, and we can agree to disagree. But yes, so what am I gonna do today? Well, you see, it's finals week, and in finals week, people study, right? At least that's what most people that want to do well in finals do. And so I am part of the crowd here, and I will review for my differential equations final, which will be this Thursday. So we've got 3 days. We got 3 days, but hopefully I can cover everything in an hour, so that you don't have to watch me stream for 3 days. Okay, what am I gonna do here? Okay, so I'm gonna essentially go over like some of the contents I've been doing, and so this class is an ODE class. Yeah, it's not an ode like poetry. It's an ODE like an ordinary differential equation. Um, and so you have various theories regarding what to do with the ODEs and how to solve them. And I thought it'd be nice to explain most of that in as quickly as possible, right? So generally, you have like some differential equation in the form of like, uh, if you say that, okay, so y and t are the variables, right? So you have some k, which is the order of uh, derivatives, and then really you can write this in the form of like some big function, right? Some big function of, let's say, y, y prime, y double prime, and then you start using k notation, yk, and then t. Yeah. So you have this thing, right? This is very general, and it's not really so approachable. Um, and then more generally, they look like some type of like function for like the y's, and then maybe some other function for the t's, and then it might be multiplied by some other function. But again, we're talking in very general terms, and maybe you might not like how general I'm speaking. So let's get more specific. Uh, a type of classification for equations depend on, number one, the order of the equation. So in this case, this would be k order, since the largest derivative is to the kth power. An alternative type of ordering is dependent on the powers that are actually contained in the expression, or the type of function that is expressing each variable. So obviously you have linear expressions, and then you have different types of functions. And so it's harder to consider the different types of functions. And so we will primarily cover linear functions because we are simple. And so a linear equation really looks something like this. So you have, again, k. So some type of equation that looks like this. And so this is a linear equation because all of the derivatives or everything concerning y is linear. And so these are just coefficients. These don't really matter as much. And so these are interesting equations. And what we want to do is find ways to solve them. And maybe not just them, but also systems of them. So you can have like multiple systems of equations with like multiple initial value conditions, like that, etc., etc. And then so you want to have like a general theory of solving this, or many like various theories in solving different types of equations. So you've probably heard of a separable equation. A separable equation is where you can write it as, say, f of y is equal to g of x dy dx. Oh, that is bad spacing. Okay, this is some separable equation. So it requires dy dx is equal to g of x f of y, or equivalently, something like that. And this is where all good things began, because this is very simple. And it's simple because you can solve the above equation just by integrating. And so while it's simple, it tells you a truth. The truth is that solving differential equations will be at least as hard as integrating. So sort of in the same sense, like solving a quadratic or an algebraic equation will be at least as hard as multiplying numbers or taking square roots or something like that. So yeah, you should be relatively comfortable taking integrals and whatnot. But so that's more so the enlightenment that you get. Now onto the main spiel. I think the first thing to start with are second order differential equations, because the theory sort of becomes similar for those with higher orders. So if you start with some second order differential equation, like that, and really now you have a few ways to solve this. You can solve this by checking, of course, the right hand side. If the right hand side is 0, then an idea that comes to mind is characteristic roots. And so characteristic roots provide the general idea to solving homogeneous equations, that is, equations where the right hand side is 0. And so it really revolves around characteristic roots plus some other method that gets you the particular solution, which either uses undetermined coefficients or annihilators, or a variation of parameters, or Laplacians, or sorry, not Laplacians, Laplace transforms. And so personally, I prefer these two methods over the other two. It's nothing like in particular. It's completely personal. I would say in terms of computational complexity, I think to rank it, of course, it would be 1, maybe 2, 3, and 4. So from least to most. Now, the annoying part about Laplacian transforms is that you have to do an inverse transform, which is somewhat like uncomfortable. And so for like simplicity, I tend to use undetermined coefficients and variation of parameters. Now onto what they really are. So essentially, if you have some linear equation, like that, then this corresponds to a polynomial of that. Oh, by the way, yeah. One thing to point out is that characteristic roots require all the coefficients to be constants. So you can't have like sines and cosines and exponents and arctangents. No, none of that. So they have to be coefficients, constant coefficients. And afterwards, it becomes a an algebraic equation that you solve. So this can have many roots. Since this is a polynomial equation, now you know from the fundamental theorem of algebra that you can always factor this up to complex roots and their conjugates. And so if you have a real root, right, if R is a solution, if R is real, then the solution is in the form of a term that looks like ae to the t, or e to the rt. If R is complex, then you get a solution of the term. By the way, you might as well write this as a plus bi. Then you get a cosine bi, or bt, plus b cosine, or b sine bt, where a, b are parameters to be determined from the initial values. So yeah, this is the most general idea on dealing with characteristic roots. And then you have like different methods. You have undetermined coefficients, which really is all a guessing game. So this starts to depend on what the right-hand side looks like. And so if the right-hand side looks something like one of the three, which I call LTE, or sorry, ATE, so 8. What do these letters stand for? Well, A stands for algebraic, so some polynomial expression. T stands for trigonometric, and E stands for exponential. And so you generally try to mimic the form. If I have like some algebraic function, then you interpolate it or guess it by finding a polynomial with the highest degree up to the lowest degree, so up to 1, with all of the coefficients as constants that need to be determined. And then if it's trigonometric, then you have a sine and a cosine. If it's exponential, then you have an exponential function. And if it's a combination of multiple expressions, then you have multiple expressions. And so it's generally about guessing, and it doesn't take that long. The other method that I will cover deals with variation of parameters. And what this really does is it also provides a way of guessing, except it's a lot more systematic and you don't really need to guess. And so I only know how to do variation of parameters for 2 variables. It's like, why don't you look up how to do variation of parameters for more variables? Well, I've been spending time on other things, and so right now I'm only focused on 2 variables. If you have an equation that looks like this, then you can do variation of parameters by finding 2 solutions to the general equation that are linearly dependent or independent. And so you do this by solving the characteristic polynomial, and then finding 2 roots, or finding 2 solutions, and then calculating the Wronskian given by this determinant, and then considering this integral, or considering the particular solution in terms of this integral given by y2, y1. Y1 is a function of a dummy variable s, hs, over Wronskian, which is also a function of s, ds, going from a to t, where a is arbitrary, minus y1 times that. Now, I think this is generalizable to higher dimensions. And I think the way to generalize this is by considering some type of linear space in an inner product, since this is essentially an inner product on the function space. But so it'll probably look like some type of either a determinant or sum of terms of linear or of inner products. Okay. And then essentially what you have are topics concerning systems of equations. So if you have like going above like different systems, how do you deal with that? Well, really, a lot of the things boil down to something called the matrix exponential, which is a matrix valued function that is like exponentiating a matrix. So here A is a matrix. And how would you go about doing that? Well, what you need to do is you need to find the eigenvalues for that matrix. Afterwards, you have a few methods. You have using traditional SVD. So if you use SVD, you can write U as the set of, or as the matrix of unit vectors. Wait, not unit vectors, of eigenvectors. Vn. And then you can find U inverse, which requires some computation. And then you can find the diagonalized matrix of exponentials of eigenvalues. So E lambda 1, lambda 2, E lambda n. And then ETA is given by U d U inverse. So that's very nice. But that doesn't work when you have roots with multiplicity, with eigenvalues with multiplicity. And so you can alternatively use Putzer's method, which gives you some type of combination of matrices. And so you do this by considering R1 given by this like smaller differential equation. dt is equal to R1 lambda 1 with R1 0 is equal to 1. Then dr2 dt is equal to R2 lambda 2 plus R1 R2 of 0 is equal to 0. And then all of that until whichever term you get. And then you have matrices B0 given by the identity matrix. B1 is equal to A minus lambda 1I. B2 is equal to A minus lambda 2I times B1, and etc. And so essentially the method tells you that the matrix exponential is the sum of Ri's and Bi minus 1's, going from 1 to n. So yeah, pretty cool. The latter is computationally more expensive since you have to solve all the small differential equations, which can sometimes be rather painful. So generally, I think I'd go for an SVD. Of course, if the system is large enough, you might not be able to find the inverse matrix. But if it's just two variables, then you can easily do that. And then so you have boundary value problems afterwards. And essentially these are differential equations with more parameters and more requirements. It's sort of like an initial value problem, except you get another value. And so here there's something called an eigenvalue problem that generally looks like this, right? And so lambda is called the eigenvalue because different values of lambda should result in different behaviors of the system. Most generally speaking, you can either get one where there's exponentials, one where there are trigs, and one where there are no solutions. Up to a condition of good solutions. And then what you would get is like y maybe 0 is equal to c y of L is equal to D or something like that. And so you can find like lambdas that satisfy these criteria by plugging and chugging and solving equations. And so this is generally what an eigenvalue problem looks like. And you can do this on different types of systems as well. It doesn't have to be a second order system. It can be a much higher order system, and you can have multiple eigenvalues. Another idea that you have for solving eigenvalue problems, not eigenvalue problems, for boundary value problems, deal with functions that are periodic. So if a function is defined on some interval that is finite, then you can actually express it in terms of sines and cosines only. Is that surprising? Maybe, but also maybe not, since, I mean, like sine and cosine, they're periodic as well. So the most general idea happens to deal with Fourier series. And so before Fourier developed the Fourier transform, or actually to Fourier's to his merit, I guess we attribute the Fourier transform to Fourier. But the integral transform is actually only inspired by Fourier and not necessarily completely devised by him. He first proposed that any function can be expressed as a series of sine functions. And then eventually people built off of that. But so if you have some function that is periodic on the interval 0 to L, and it doesn't really matter if it's inclusive or not, you can express it as a summation of sines. Here, this, so an cosine n pi k pi x over L plus bn sine k pi x over L. So yeah, sines and cosines, you can break it down pretty easy. And then there's the idea of matching a few terms together. So c sine, cosine, and then a bunch of amplitudes. And then you might think, oh, well, might be better off just expressing this as a complex function. That is exactly the idea. So what am I writing in terms of n? You can also express this as ck of e to the I k pi x over L. And then ak is ck plus c negative k over 2. bk is ck minus c negative k over 2I. And you can calculate AKs and BKs with a few formulas that deal with the orthogonality of the function space. But so you might as well start with A0. Since if you notice in this expression here, when k is equal to 0, the sine term blows up, or the sine term disappears really, does not blow up, it just fades away. And the cosine term also becomes 1, so this is a constant. And this constant is given by 1 over L, if you integrate over the period, of fx dx. And the integrands, the boundaries of integration remain rather similar. And so for ak, it's just this times 2. let's just write n. I don't like k. Yeah, so the integrals remain rather similar. And so going from this, you can sort of write Cn as, I think you can write 2 over L of 0 to L f of x e to the I pi x over L dx, which should give you a real valued expression times a complex constant. All right. That was dealing with Fourier series. Okay, I think this provides an overview of what I will encounter in my class, in my test. Obviously, there will be other things that I will encounter and that I'll have to prepare for, but this is what is in my head right now. So I've emptied it. It's all yours now. All right, have fun.